Imagine you just hired the most advanced sci-fi superintelligence in the world to be your personal research assistant.
Yeah.
Like, it has read the entire internet. It can write poetry. It can code, pass the bar exam.
Oh, totally. A complete digital powerhouse.
Right. But then you ask it a highly specific factual question, and instead of using its massive neural net to just sort of ponder the answer, it calmly reaches under the desk, pulls out a dusty green screen computer terminal from the 1970s, and starts typing out vintage Unix code.
Which is such a wild visual, honestly.
It really is. Welcome to the Deep Dive, everyone. Today, our mission is to give you a shortcut to understanding a massive and, frankly, surprising shift in how artificial intelligence searches for facts.
Yeah, we are looking at a stack of state-of-the-art foundational Gen AI papers today. Specifically, we're zeroing in on a really fascinating new research paper titled GrepSeek, Training Search Agents for Direct Corpus Interaction.
Which is a mouthful, but we'll break it down, because it basically flips the conventional wisdom of the last few years totally on its head. I mean, the entire tech industry has been obsessed with making AI understand human language in this fuzzy conceptual way, right? Like trying to mimic human intuition.
Exactly, trying to make it think like a human brain. But this new breakthrough, GrepSeek, actually involves teaching an advanced AI to use old-school command line tools from the 70s. We are talking about programs like grep.
Which, if you're not a programmer, grep is what software developers use to find exact, literal strings of text inside massive folders of code.
Right. It's very rigid, very exact.
So if you are listening to this and you've ever been frustrated by an AI giving you a confidently wrong, slightly fuzzy answer, a hallucination, this deep dive is going to explain exactly why that happens. And, more importantly, how researchers are fixing it by treating the AI less like a philosopher and more like a strict filing clerk.
To really appreciate why GrepSeek is so necessary, we first have to look at the current flawed paradigm of AI search. It's known as agentic RAG, or retrieval augmented generation.
Yeah, let's unpack RAG a bit. Because when you type a prompt into a standard AI today, it isn't literally reading through the raw text of Wikipedia in real time.
No, not at all. It's not reading in any traditional sense. In a RAG system, a completely separate AI model has already processed all the reference documents in advance. It reads them and converts them into what we call dense embeddings.
Dense embeddings, right.
Basically, it translates sentences and paragraphs into massive lists of numbers, or vectors. And these numbers represent the semantic meaning, or honestly, the vibe of the text.
The vibe. I love that.
It places the document in this huge, high-dimensional mathematical space. So when you ask a question, the system translates your question into a vector, and then it searches its index for documents that point in the same mathematical direction.
So it's looking for a conceptual match, not a literal one. Okay, let's unpack this with an analogy. Our RAW is kind of like going to a massive hardware store, right? You walk up to an employee and describe, hey, I need a small, silvery thing that holds wood together.
They get the vibe of what you're asking.
Right, but they might bring you a nail, or a screw, or maybe a staple. They understand the broad concept of a fastener. But direct corpus interaction, the method GrepSeek uses, is entirely different. It's like walking into that same hardware store with the exact 12-digit manufacturer part number and just walking straight to aisle 4, bin 12.
That is a perfect way to put it. Dense embeddings are incredibly powerful for broad concepts, but they really struggle with exactness. They sort of smooth over fine details to create those big, overarching concepts.
Right.
So GrepSeek just completely discards that pre-computed index of numbers. Instead, it treats the raw text corpus-like. In this study, they used a massive Wikipedia file containing 21 million passages. It treats that raw text as a live environment.
It's actually in there hunting.
Exactly. The AI agent actually writes and executes surgical shell commands in the terminal. It uses a tool called URGE, which stands for RipGrep. So if it wants a specific chemical formula, it doesn't look for documents that feel like chemistry. It searches the raw text file for that exact string of characters, byte-level precision.
Okay, so the precision makes total sense. But if I'm thinking about this critically, the causality here seems like a huge hurdle.
Oh, it is.
Because language models are fundamentally built to chat. They are, at their core, probability engines predicting the next word in a sequence. So how on earth do researchers actually train a conversational AI to reliably write rigid Unix shell commands without hallucinating broken code?
It's a massive challenge.
I mean, writing RGF and piping the output into head command requires absolute syntactic perfection. If it is a single misplaced bracket, the terminal throws an error and the whole search breaks, right?
Right. And if you just take an off-the-shelf AI and let it loose on a raw text file using basic reinforcement learning, the results are completely chaotic.
Really? Like what happens?
Well, the model writes overly broad commands. Like, it might just search for the word "the," which obviously retrieves millions of lines, overloads the memory, and crashes the entire system.
Oh, wow. Yeah, that would do it.
So to solve this, the researchers built a very specific two-stage training pipeline for their model, which is based on the Qwen 3.59b architecture. And the first stage is where they generate a cold start data set using a really brilliant methodology called the answer-aware tutor.
Okay, the answer-aware tutor. I want to highlight this because this is where the innovation feels almost backward. The tutor model is given the final ground truth answer right from the start.
Yes, it starts at the end.
So if the question is, who won the World Series the year the iPad was released? The tutor is just handed the answer, the San Francisco Giants. And then it works backward.
Exactly.
It figures out what the final document retrieved should be, so the 2010 World Series page, and what terminal command would find it. Then it figures out the previous step, finding the iPad release date, and chains it all the way back to the original question.
It's reverse engineering the truth, essentially. Finding the logic path.
But wait, I have to push back on this. Isn't that cheating? I mean, if it already knows the answer, how does it actually learn the skill of searching? It's like teaching someone how to solve a maze by just dropping them at the exit and having them trace the path backward to the entrance.
Right, you're just showing them the solution.
Exactly, you aren't teaching them how to navigate blind corners.
Well, the researchers completely anticipated that exact problem. If the AI learns to search by simply querying the answer it has been handed, the training is useless for real-world applications. So, to counter this, they enforce a really strict answer masking rule.
Answer masking.
Yeah. When the tutor is building this backward path, the system physically blocks it from using the actual answer, or any known aliases of the answer, as search terms. It is forced to find the target document using other contextual clues from the surrounding text.
Ah. Okay, so it builds this verified path backwards, but it avoids the forbidden words?
Exactly. But, as you pointed out, when you actually use a search agent as a user, it has to move forwards. It doesn't know the future state of the data.
Right, it doesn't have the answer yet.
Which brings us to the second phase, forward assembly. Once that backward path is verified, a completely different model called the answer-blind planner takes over. And this model only sees the initial user question and the history of what it has successfully searched up to that current moment. It has to generate the reasoning and the terminal commands moving forward.
And if it gets stuck, or if it suddenly starts referencing information it hasn't actually retrieved yet.
Which happens, the researchers call that future state leakage. And when it does happen, the system intervenes. The tutor steps back in, looks at the planner's flawed reasoning, and edits it so that it remains causally grounded in the present moment.
So the tutor is essentially acting as a guardrail.
Precisely. It forces the planner to acknowledge, hey, I don't have that piece of the puzzle yet. I need to issue a new grep command to find this specific clue first. This rigorous back and forth creates this pristine data set of forward-moving, highly logical search trajectories. The AI actually learns the step-by-step causality of an investigation.
And then, once they have that pristine data set, they run it through a reinforcement learning phase using something called Group Relative Policy Optimization, or GRPO.
Right. Because standard reinforcement learning just rewards a model when it eventually gets the right answer. But GRPO is much more sophisticated.
How so?
For every single question, the policy generates a group of different possible search trajectories. Say, 5 different ways to find the exact same fact. Then it compares them against each other relatively. It scores them to see which path was the most efficient and which commands were the most precise.
Oh, so it's not just rewarding the correct answer, it's rewarding the formatting too. Because the environment requires the commands to be wrapped in specific XML tags, right? Like the formatting you see on a web page's source code. The AI has to output angle brackets, then the word command, then the actual grep command, then a closing tag.
Yes, the syntax has to be flawless.
If it gets the exact right answer but forgets the closing tag, the shell environment can't read it. It just sees raw text. So in GRPO, if that formatting is broken, the AI gets a reward of 0, no matter how good its underlying logic was.
It forces the model to be a disciplined, tool-using agent rather than just a chatty bot.
Okay, so I get the training logic. It creates an incredibly strict agent. But if we connect this to the bigger picture, I see a glaring logistical flaw. The researchers are using a raw Wikipedia text file that is 14 gigabytes in size.
It's massive.
Yeah. Running a standard Unix command sequentially through a 14 gigabyte file every single time you ask a question has to take forever. You're limited by disk read speeds. You can't have a user waiting 10 minutes for the cursor to blink while the system reads every line of Wikipedia from A to Z. How is this practical?
It wouldn't be if they did it sequentially. To solve this bottleneck, the researchers developed a semantics-preserving sharded parallel execution engine.
That's quite the title.
It is. But what it means is they take that massive 14-gigabyte corpus and break it into 32 separate disjoint shards along strict line boundaries.
Okay, here's where it gets really interesting. It's the difference between you reading a 10,000-page book cover to cover to find a single quote versus ripping the book into 32 equal chunks and having 32 of your friends read them simultaneously.
That's exactly how it works. When the AI agent issues a shell command, the execution engine analyzes it before running it. If it determines the command is stateless, meaning each line of text can be evaluated independently without needing to know what the line above or below it says, the engine dynamically routes that command to parallel computing threads. All 32 shards are searched at the exact same millisecond.
Wait, but if the command is searching for the top results, the math gets a little messy. If I tell my 32 friends to find the top 3 mentions of a word in their individual chunks of the book, they're each going to hand me 3 results. I'm going to end up with 96 mentions. The system must have a secondary mechanism to filter that down.
Good catch. That is where the semantics preserving aspect comes in. The engine uses specific reduction rules. The AI might ask for the top 3 results by piping its search into a head might and then 3 command. Just like in your example, each of the thung2 parallel threads finds its own local top 3. The engine then takes those 96 results, concatenates them into a single list, and applies a final head minus then 3 command over that compiled list.
Ah, so it filters the filters.
Exactly. This guarantees byte-exact equivalence. The AI gets the precise mathematical result it would have received if it had searched the entire file sequentially, but the time saved is staggering. Tool latency drops from 5.39 seconds per query down to just 0.71 seconds.
Wow, okay. That speed definitely makes it viable for an end user waiting for an answer.
And the real-world win for the tech industry is the memory footprint. A standard dense retriever, like the one driving RAG models, requires 221 gigabytes of RAM just to hold its pre-computed semantic index in active memory. GrepSeek only requires 14 gigabytes.
That's literally just the size of the raw text file itself sitting in memory.
Yep. Plus, you entirely bypass the indexing phase. Building a dense vector index for 21 million passages takes over 62 hours of expensive GPU compute time before you can even ask your first question. With GrepSeek, 0 indexing. You just point at the raw text file and it goes.
Okay, so I'm completely sold on the speed and the cost, but I demand proof of the actual intelligence, because if this is just a glorified Treetroll plus F keyword search, how does it beat sophisticated semantic AI on hard questions?
Well, the proof is in the queries. The paper benchmarks GrepSeek against 7 different open domain question answering datasets, and they really focused on multi-hop reasoning tests, like HotPot QA and 2Wiki multi-hop QA.
For our listeners, think of these multi-hop datasets as obstacle courses for AI. The question can't be answered by reading one paragraph. The AI has to find an initial clue, extract a secondary entity, search for a completely different article, and then synthesize the facts.
Right, and on these rigorous benchmarks, GrepSeek achieved the strongest overall token-level F1 and exact match scores. It completely destroyed highly trained agentic R-Gray systems.
And a high F1 score basically means the model is both highly accurate, like they didn't hallucinate junk, and highly comprehensive. But how? Can you give an example?
Yeah, the case studies are fascinating. There is a specific example involving a chemical formula. The prompt asks the AI, which component of shellite has the formula NCOH?
Okay, so a very specific literal string of characters.
Exactly. When the dense retriever RAG models got this, they translated that chemical formula into a semantic vector. But you cannot summarize the literal characters of a chemical formula as a broad concept. The mathematical vector ended up plotting into this generic chemistry-shaped region of the semantic space.
Ah, I see where this is going.
Yeah. The RAG system retrieved documents about dinitrophenol, which happens to be a different chemical component of the explosive shellite. The context was very close, but the factual answer was entirely wrong.
So the AI grouped the concepts together because chemistry papers all use similar terminology. It became a blurry, conceptual blob. But GrepSeek doesn't use vectors.
No, it used the RGF command. The RGF flag stands for fixed string. It bypassed semantic meaning entirely and told the search engine, find the exact sequence, open parenthesis ON, close parenthesis CHOH. It instantly bypassed all the generic chemistry documents and perfectly isolated the document for picric acid, the correct component.
Wow. And there was another example you mentioned earlier, right? The Red Dead Redemption developer?
Yes, dealing with entity precision. The question asked for the specific company that developed the video game Red Dead Redemption. When RE searched its index, the vectors for the parent company, Rockstar Games, and the specific subsidiary, Rockstar San Diego, were mathematically almost identical. The retriever smoothed over the distinction and just delivered the broader parent company.
Because they have the same vibe. But GrepSeek, filtering iteratively, found the parent company, found the game title, and then ran a strict filter for the specific word developed, zeroing in on the exact phrasing to find Rockstar San Diego.
Exactly.
So what does this all mean for the user? It means when you need to know if the lead singer of an obscure band's dad won the highest index rating versus the National Medal of Science, GrepSeek's surgical precision prevents the AI from falling for semantic close enoughs.
The precision really is unparalleled. But, and this raises an important question, that exactness is a double-edged sword. As powerful as direct corpus interaction is, what happens when human language isn't exact?
Right, because dumb search fails when things get messy.
It really does. The paper outlines distinct limitations. GrepSeek struggles significantly on datasets like PopQA.
Which rely on long-tail entities, right? Obscure trivia, rare names.
Yeah, because GrepSeek relies entirely on explicit string matching, it is hypersensitive to surface form variations.
So if I misspell a word or leave off an accent mark on a French name, the whole search breaks.
Completely. A dense embedding model naturally understands that the word with the accent and the word without the accent represent the exact same concept. GrepSeek does not. If the byte-level string isn't an absolute match, it returns nothing.
That's a huge blind spot.
And there is another severe limitation in how Unix command line tools return their results. They do not rank documents by semantic relevance. They simply return results in the order they appear in the file.
Oh, right, because Wikipedia is organized alphabetically or chronologically in the raw data file. So the tool is just reading from top to bottom.
Exactly. The paper highlights a defining failure related to this with Citibank. The AI needed to find the founding year of Citibank. But early in the massive Wikipedia file, under the letter R, there was a long article about a film company called Relativity Media.
Okay.
And deep in the text of that article, it casually mentioned that the company had secured a loan from Citibank.
And because the AI used a head command to limit its results and save memory, literally telling the computer to stop reading after it finds the first few matches, it hit that random mention of Citibank in the Relativity Media article and stopped searching.
Right. It never made it down to the actual C section of the file where the core Citibank article was located. It got stuck analyzing the film company's loan history, trying to find a founding year. Dense retrieval easily won that round because semantic vectors inherently understand which document is the primary, most relevant source for a given entity.
That makes perfect sense. So connecting this back to you, the listener, when you need the vibes, the broad context, or you need the system to navigate typos, you want semantic search. But when you are looking for an exact financial record or a highly specific chemical formula or a unique line of code, you want the absolute rigidity of GrepSeek.
Precisely. We've seen today how teaching a modern AI to use vintage Unix commands creates this lean, mean, hyper-precise search agent, one that saves massive amounts of memory and outsmarts semantic AI on exact details. But the paper's conclusion makes it clear. The future isn't a binary choice.
It's a hybrid architecture, isn't it?
Yes. Combining direct corpus interaction with index-based semantic retrieval, seamlessly switching between the two depending on what the query needs.
It's fascinating. We have spent years trying to make artificial intelligence think more like human brains, fuzzy, intuitive, and conceptual. But if the ultimate fix for AI hallucinations is forcing it to sit at a virtual terminal and search like a rigid 1970s computer program.
A total regression in a way.
Yeah. Maybe the key to perfect artificial intelligence isn't making it more human, but reminding it that it's a machine, something to think about next time you hit search.